Good afternoon. I'm Arun Serafin, the Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. I want to thank all attendees for your support of NDIA and ETI and for joining us for today's webinar, Modular Open Systems Architectures, MOSA 101, with Dr. Evan Fortunato. This webinar is part of our Tech 101 series, where we present complex technological concepts as introductory webinars with a focus on their national security implications. Modular Open Systems Architectures, or Modular Open Systems Approaches, or MOSA, is more than a defense acquisition buzzword. It's a practical and commercially accepted framework for managing complexity and encouraging innovation throughout a product's lifecycle. By applying modular and open constraints to systems designs, MOSA enables flexibility, faster upgrades, and broader competition. Congress and DoD have both attempted to drive more use of MOSA within DoD through laws, directives, and guidance in the hopes of improving acquisition results. Today's session will break down what MOSA is and what it is not, how it works in practical terms, and why getting it right matters more now than ever. Some administrative items before we get started. All attendee lines are muted. If you have a question during the webinar, you can submit your question in the question box in the webinar panel. You can submit questions during the presentation, and we encourage that. We will do our best to get through all the questions during the Q&A portion of our session. We are recording today's webinar for members unable to attend and plan to post it on our YouTube channel as soon as possible. To introduce our speaker, Dr. Evan Fortunato is the president and CEO of Apogee Research, where he works on smarter systems integration through innovative software solutions and systems engineering approaches. He earned a PhD in nuclear engineering from MIT and has worked in government as a DARPA program manager, where he led the development and delivery of the Stitches capability throughout DoD, as well as working in small, medium, and large defense technology companies. It's great to have Evan with us today. He's a world-renowned expert in the field of MOSA. We've had a chance to work with both Evan and Apogee in the past. One of his colleagues, Jessa Lee, actually was a presenter at one of our Tech 101s maybe a year or so ago. I've had a great chance to work with Evan over the years when I was on Capitol Hill. He's really a trusted source about these kinds of complex technological issues. And he's also been great supporting other ETI events, including our joint event with the Hudson Institute on interoperability. So with all that, we're expecting great things from you here today, Evan. Thanks for doing this, and I'll turn it over to you.
Great. Thank you, Arun. Thank you to everyone at ETI and NDIA for hosting this. I'm just going to go ahead and share my screen to get this started, and hopefully this will work. And everyone, or Arun, can you confirm that you can see the screen?
Yep, we're good.
All right, fantastic. So as Arun mentioned, a little bit about my background. I'm an engineer at heart. I've got a physics undergraduate and a nuclear engineering PhD, both from MIT. Professionally, I entered the national security space since 9/11, and I haven't left. Arun has covered most of this. I'll say that I've transitioned many systems from research into operational use, and most of them have used MOSA as an approach for making viable, complex systems that work in real-world settings. I'm going to give a caveat before I get into the actual webinar material, which is my views on MOSA are not the standard views on MOSA. It's not what you're going to find in schools. It's not what you're going to find from a web search or even in the DoD guidance. It's often in conflict with those things. I will say I'm a huge fan of MOSA, and when done right, it is an important element of an engineering approach. But MOSA is easy to do wrong, and doing MOSA wrong is often worse than not doing MOSA at all. It's a bit like seasoning. A pinch of salt is great. A cup of salt ruins the dish. So the core benefits of MOSA is managing complexity and creating market efficiencies. And I'm going to keep harping on those two themes of managing complexity and creating market efficiencies throughout the discussion. All right, so let me start by breaking down the words. Modular open system architecture. Well, that's a system architecture. What is a system architecture? So when we think about the space of solutions for a problem, for almost any problem, that space of solutions is going to be remarkably large. There are often constraints that we want to add to the original problem to guide the solution one way or another. And without providing those constraints, you typically don't get a solution to the stated, you get a solution to the stated problem, but not the solution you want. The context really does matter, and the engineering teams have to understand that context to be effective. So system architectures provide the system level constraints on possible solutions to guide the developers. Typically, it excludes bad solutions rather than requiring particular solutions be included. And this is critical to give engineering teams the degrees of freedom, the flexibility to innovate and come up with new and better solutions. And that's key in MOSA, is that we exclude things rather than require things. So just as throughout the talk, I was told that I should give real-world examples rather than DoD-specific examples. I'll tie it back to DoD thoughts, but I'm going to try and keep it on simple real-world examples. So example problem, I need to eat dinner. Example constraints, I don't want to cook, or I'm a vegetarian, which I'm not, but it makes a good example. So I don't eat meat. Similarly, if I want to be able to brew coffee at home, I don't want to have to go to Starbucks every day. Constraints, I don't want to own a grinder. It's too loud, too annoying. Single serve is sufficient. And so this is how we think about problems and constraints. And when we think about MOSA as a particular set of constraints, system architecture constraints, we'll want to understand how that influences how we build these systems. So another slide on constraints. We often think about good constraints and bad constraints as if there were some universal definition of good and bad. And to sort of hit the punchline at the bottom of the slide, constraints being good or bad really depends on the problem. There's no universally good set of constraints, though you might argue there's some universally bad set of constraints. So just going through some trivial examples, the three little pigs. You're going to build a house out of straw or wood or bricks. And in the case where you're trying to stop a hurricane force wolf wind, bricks make a lot of sense. But most of the houses in the US are built from wood for good reason, because it's more cost effective, it's more maintainable in some ways, etc. So the constraints matter on the problem you're in. Using other examples, Tesla takes a very different architectural constraint than other car manufacturers do for autonomous driving. Most car manufacturers use a combination of visual sensors and something called LiDAR, which is similar to radar in that it tells you the range to an object. But Tesla, through Elon Musk's decree, has said that humans drive with only visual sensors, and that means autonomous systems should be able to drive with visual sensors, and so put a system constraint that there's no need for LiDAR. And time will tell whether this particular constraint is a good one or a bad one. Similarly, on the software side, we've seen a migration in the last 10, 15 years from on-premises large scale software applications into cloud-based microservices, where we sort of break everything up and move them to the cloud. And while that can work really well in some cases, it actually works really poorly in others. And there are many documented cases where it works well and where it works poorly. And critical systems require redundancy. We see this all the time. You might want to have a backup power supply such that if your main power supply goes down, you can switch over to the other one, replace the bad one, and never have your system go down. But if you don't require that, if you're perfectly fine turning your laptop off at the end of the day, having all that redundancy just adds cost and complexity and weight and things you don't need. So when we think about these constraints, we've got to understand when do the constraints apply and when they don't. And this becomes important for MOSA. MOSA isn't a cure-all, and MOSA shouldn't be used everywhere in the same way. It's got to be tailored to each of the problems we're looking at. Okay, so finally we get to the first part of MOSA, the modular part, which is a particular type of architectural constraint. So modular constraints are appropriate for problems that aren't fully coupled. It allows you to solve the problem in parts. You solve part one, you solve part two, and then you bring those parts together to form the full solution. And this is what reduces the complexity, because each problem can be solved individually. Now, this is especially critical if the different parts require very different skill sets. But it's key that you only need to provide minimal information between the different parts, typically via their interfaces. If you need to share all the information between all the different modules, you're not actually doing a modular problem. And your original problem is probably more fully coupled than you appreciate. And MOSA is probably a really bad idea for situations like that. So let's come back to that coffee example. You want an expert in coffee to decide what beans and how you roast them and maybe how you grind them. And you want an expert in consumer electronics to build the actual coffee maker. And in general, the overlap of those skills is not high. If you used a coupled solution, then you would need an expert, maybe an organizational expert, but an expert that can handle both. And it will stop you from mixing and matching. And we see that. Coffee solutions tend to provide a modular solution. You buy the coffee maker from a company that makes consumer electronics, like Cuisinart, and you buy the coffee beans from a company that makes coffee beans, not making consumer electronics. So a comment about modular solutions and how good they are. As a general rule, modular solutions are typically suboptimal, meaning they're not the best possible solution if you were willing to put in unlimited time and effort. And we see this with coffee. If you want to have the best possible cup of coffee or cup of espresso, you might do a much more complicated machine that relates how you grind the beans and how you pack the grinds and how you heat the water and the flow rate of the water through the beans, etc. And that might give you a better cup of coffee. But modular solutions are often particularly effective and often the best in situations when you've got fixed resources, time, money, and if you've got changing requirements. Those are the places where MOSA and modularity in particular really shine. And later on, I'll get to some concrete examples of this to help try and make this point more concrete. And obviously, when you couple the modularity with the openness, you can have some significant benefits for market competition. But again, only if you're willing to accept the suboptimalities and if your problem is actually modular in its nature. It's not a fully coupled problem. Okay, so continuing on with the coffee theme, because I like coffee, what are the modular interfaces of a coffee maker? Well, it turns out they're different for the different coffee makers, but they all sort of resemble each other. So there are many different standards of coffee makers. I've shown 3 of them here. The traditional drip, which dominated forever, Keurigs and espressos, but there are others. But these 3 give you a good sense. And if we think about the traditional drip, that was a standard that lasted for a very long time. And it sort of all looked the same, whether you were buying a Mr. Coffee or Cuisinart or any other brand. You had a water tank and a heater. You'd heat the water and push it up into a basket, which contained a filter with coffee grinds in it. The water would flow through the coffee, through the filter, and into a carafe with maybe a heating plate at the bottom. And that provided a nice modularity. That basket was where you put your filters and you put your coffee grinds, and coffee makers sort of understood what the normal parameters were, and they could give suggestions about how much coffee versus water to put into the basket. But you often had to tune it a little bit for your particular coffee maker if you wanted your best cup of coffee. But the market shifted. People wanted more single serve. They wanted more tailored coffee. They wanted different cups for different people. And so new standards emerged. Take Keurig, for instance. It sort of looks like the old standard in a lot of ways. If you cut open one of those K-cups, you'll see that there's a little basket with a filter and coffee in the basket. And when you put it into the Keurig machine, it punches a hole in the top to put hot water through it, which goes through the coffee, goes through the filter, and then a hole in the bottom to let it go into your cup. An espresso, it looks a little different, like the Virtuo pods. They spin at high speed to get the water to go through the coffee at pressure. So in each of these cases, there is a modularity, but the modularity is different. They've chosen different standards and different instances of modularity. Now, the modularity is still there, and that gives them the complexity management that they're looking for. But the point is it doesn't have to be common. And in fact, if it were common, we'd have a problem. Imagine that we all agree that the traditional drip, which was the dominant standard, had to be the standard. Well, then we wouldn't get Keurigs and espressos. And we'd end up stagnating on an old design choice and an old solution. And this pattern repeats again and again. It repeats in the DoD everywhere, but even in the commercial world, it repeats again and again. So VHS was the standard until DVD and then streaming, and manual transmission was the standard until someone started using automatics, and then people found that more convenient. Combustion engine was the standard until hybrids and EVs came out. And we see in the commercial world how even modular solutions with a very, very well adopted standard break those standards and evolve over time. And in fact, that gets to the heart of the issue with modularity, which is standards. And for a lot of people, they believe standards are the part of modularity that makes it work, when in fact, standards are actually the problem with the modular approach. To be modular, you need to share information, hopefully limited information, between the different modules. And traditionally, this is done via a standard interface, an agreed upon interface that's common between the sender and the receiver. But these standards are what create barriers to innovation. So if we think about DoD, it still uses Link 16, a communication standard created 50 plus years ago, which is a little bit crazy. Just imagine using a phone based on a standard from 50 years ago. It's unimaginable to us. And the funny thing that occurs is the more commonly adopted the standard, the harder it is to innovate away from it. So the internet still uses IPv4, which is a very old standard, even though IPv6 was designed long ago and launched 10 plus years ago and is clearly the better solution. But it's hard to get off the standard once they've been adopted. And that's what retards innovation and retards advancement. TVs are another good example of this. We had 4:3 ratio TVs until the 1990s, but switching to widescreen was hard because most of the sources, the other half of that interface standard of the modular interface, things like VHS and broadcast, were still 4:3. So even if you bought your nice new widescreen TV, your 16:9 widescreen TV, you're still watching your Who's the Boss on a 4:3 ratio, and those black bars are just wasting space. So all those early adopters were not getting real benefit. Now, in the commercial world, those early adopters do lead the way and show how much better the new solution is, and that eventually leads to a breaking of the standard. But again, the standard should be viewed as a necessary evil at best of modular solutions. It's not a feature to be lauded. It's not the way you get what you want. It's the way we currently get what we want and have to deal with. And later on in the talk, I'll talk about some other options that allow you to achieve MOSA without relying on the common standard. All right, before I get to openness, I want to do one more slide on modularity. And this is just a slightly more complicated example to give you a sense of what it looks like to be fully coupled or fully decoupled or partially coupled. And the example I'm going to use is blackjack at a casino. So when we think about blackjack at a casino, we can take three different approaches. We'll start with the fully coupled one, which I think of as the sort of traditional DoD approach. We set some high requirements. We need to be optimal performance against a capable adversary, in which case the casino house. And so we're going to take a solution where we're going to record every card that's been dealt. We're going to reason over all the possible outcomes, optimize across all the possible bets. And the result is an extremely highly performant system for the situation it was designed for the initial requirements. But it's extremely resource intensive. It's hard to develop. It's hard to maintain. It's hard to evolve. And it's easy for the house to counter. They start changing the number of decks in the shoe. They start randomly reshuffling the decks. And very quickly, this falls apart. And all that investment is lost. And this was the problem with DoD development that MOSA really tried to solve. Now, on the other side is the fully decoupled approach, which I'll jokingly call the Silicon Valley approach. Stateless microservices that scale. We don't want all this complexity. We want a simple heuristic that's independent of the past plays. You open up your app on your phone, you punch in the numbers, and it tells you the answer. Small, simple, scalable profit. Except that you don't win as much. In fact, you probably don't win net at all. You lose. And that's the challenge with the fully decoupled solutions, is that this isn't a fully decoupled problem. It's a partially coupled problem. And if you treat it like a fully decoupled problem, you get bad answers. And I've given the standard heuristic that if your hand value is low, hit. If your hand value is high, stand. And if your hand value is in the middle, look at what the dealer has to figure out what to do. Now, the last one is the modular coupling. It's MIT's response. And if you don't know what that means, you should look at one of the books or the movies on this topic where a bunch of MIT alums and students decided to beat the house at blackjack, and they did. And while the description I have here is a slightly simplified version of what they did, it captures the essential elements. So what they constructed was a solution that had two modules, a card counter and a big better, with very limited interface between them. In fact, just a couple of bits is enough. So the card counters sit at every table, and they watch the cards coming out. They bet a small amount of money just to sit at the table. And instead of memorizing every card that's been dealt, they do something really simple. Like if the card is high, add 1. If the card is in the middle, add 0. If the card is low, subtract 1. And now, if you just keep track of that very simple count, you can tell if the deck is biased, if a lot of the high cards have been played, and therefore there's going to be more bias towards the lower cards, or if a lot of the low cards have been played, there'll be more bias to the high cards. And whenever the deck becomes sufficiently biased, the card counter can signal one of the two bits to the big better to come over and play the table. Now, of course, they also need to signal whether the deck is high or low to the big better, so the big better knows how to bet. The result of this is an extremely performant, decoupled, and hard to counter modular solution. Because each of the roles is simplified, if the house catches one of the card counters, they can simply replace it with another student. Because the interface is very, very small, it's hard to detect the communication between them. It can just be a scratch of the cheek or adjusting of the glasses. And because you've captured the essential information, the bias of the deck, the net bias of the deck, it's enough to allow the big bettors to actually win significant amounts of money. And that's exactly what the MIT teams did over many years. It's a great story. If you haven't read it, it's worth reading, but it really is beautiful in how it captures how a partially coupled problem is well solved by modular solutions. Okay, so with that, I'm going to jump over to the open side, which is a little simpler than the modular side. The modular side is the more important of the two constraints. And by open, we mean that the information that is exchanged between the modular components is known to the people who need to build the modular components. If the companies that manufacture coffee filters don't know the dimensions of the basket, it gets really hard for them to manufacture the coffee filters. And similarly, you need to know which version of USB your electronics use for charging, including things like the amperage and the protocol. And a word of warning here, we often describe USB as a standard. It probably shouldn't be described as a standard. If you think about USB, from the physical perspective, there's A and B and mini and micro B and C. And then within a given one of those, like C, there's 2.0, there's USB 2.0, there's 3.2, there's 3.2 faster, there's 3.2 even faster, there's 4.0, there's 4.0 faster. I'm sure there'll be a 4.0 even faster. There's DisplayPort, there's all these different variants. So USB is not really about the standard, because it isn't really a standard. It's about openly publishing the interface specifications of the heterogeneous set of standards that are in play. And that's important to remember as we go further down into the talk, because people will often use USB as an example for why we should have a common standard when we shouldn't. So obviously, open doesn't have anything to do with publishing information on the open internet. You can have classified open systems, which are only known to people with the right clearances. You can have authorized partners in a commercial setting that only have the information if they are authorized, and it's not available to the broader community. But oddly enough, the open constraint does require that you know and document your interfaces. And while that seems rather obvious, this is often the problem in DoD systems, because they document their design, but then when the engineers try and build the system, they discover errors that weren't foreseen by the designers and have to make changes. And if you don't capture those changes in an as-built documentation, the documentation of your interfaces is often very different than what's been implemented. In my experience in DoD systems, the vast majority of DoD systems don't know what their actual interfaces are, and you have to spend a significant amount of time reverse engineering the real interfaces from what they think it is before you can actually start the integrations. And the underlying root problem here is not that people are incompetent or people are lazy. It's that documenting interfaces is a longstanding problem. English is fundamentally a terrible language to document an interface. And we don't really have a language that's complete for documenting interfaces. And in fact, I don't think we can have a language that's complete for documenting interfaces. So a bit more on this later. So what are some of the advantages and disadvantages of open constraints? Well, the main benefit is improved market competition. If properly documented, an open modular system can have each of the modules competed separately, and that has huge advantages. It allows orgs, especially smaller orgs, that are expert in one or more of the concerns, but not all of them, to still provide their value to the community. There's some great coffee roasters that don't know the first thing about building consumer electronics, and they shouldn't need to know something about building consumer electronics in order to make great coffee. And you see these themes come up in the DoD a lot, where if you're not a prime, if you can't build the whole system, it's really hard to supply just a single component. But the problem with the open constraints is that you hit problems of backwards compatibility. So once you've established that open modular system, if you change the modularity, if you change the interfaces, the standard on which that modularity is built, you break backwards compatibility. And what this does in practice is it creates a standards lock, which can cripple an organization's ability to innovate. And the DoD suffers from this almost everywhere. It's the main problem, in my opinion, with the way that DoD does MOSA, is that it moves from a vendor lock problem to a standard lock problem. And the standard lock is actually more pernicious and harder to get out of than the vendor lock was. But it's also true in the commercial world. And we've seen this time and time again from great companies that had huge market shares, and locked to a particular standard. Polaroid is the best example of this, with a Blockbuster and IBM PCs and Blackberries and Palms and Kodak film and even DEC, for those of you who remember it, the servers with the VT102 terminals. They all got locked into their view of what the standard should be. And when the industry started innovating, they stayed locked to their view so they wouldn't break backwards compatibility. And the result was they lost their market share, or in many cases went out of business. And this problem is most pronounced when the interfaces are mandated, preventing innovation by policy. And this can be true when it's mandated, for instance, by the government, like it is with Europe and USB-C, or it's mandated by a customer, like it is in the DoD, or it's mandated by a CEO. There are many stories of companies like Polaroid where engineers recognize the new innovation, but the CEOs by policy wouldn't allow that to occur. So the goal is to achieve market competition, but to do so without creating that ossification effect, which the standard lock causes. Okay, so we've talked about modular, we've talked about open as two types of constraints, system architecture constraints, and how they come together to, in some cases, give significant advantages in reducing complexity and increasing market efficiencies. But let's talk about how this all comes together in real systems. And before I can talk about the forms of architectures used today, I want one more slide to set it up, which is a combination of proliferating standards and generating post facto interoperability in the context of child's play. So on the left, we've got XKCD, which is often brilliant. Those of you who don't read XKCD, I highly recommend it. This is a really old XKCD 927, how standards proliferate. And it really captures the point beautifully, which is there are many competing standards, and there always will be. And every time some person or group of people think this is ridiculous, they're all dumb, we should just make the one universal standard that covers every case. The result is we end up with 15 standards. We end up with one more standard, but it doesn't solve the problem. And the reason why is because different problems require different modularity, and therefore different standards are most appropriate for those different modularities. And when we attempt to make a standard that rules them all, it either doesn't, or even worse, it adds so much ambiguity and complexity that it doesn't act like a standard anymore. So what is the option if we have this proliferation of standards and everyone is using their own? And we can describe this in technical terms, and I can talk about software and optimizing compilers and auto-generating code, but that's really hard to visualize, and ones and zeros are pretty boring. So I'm going to use a visual analogy, which is children's toys. And if we think about children's toys for building things like Legos and Lincoln Logs and Kinects, and I don't even know what that bottom one is, they don't really normally interoperate with each other. So we think we have to choose one of those standards and lock into one of those standards. But imagine that you had people who would produce components that were half Lincoln Log and half Lego. And these graphical representations are obviously not optimal, but they're easy to see. So now, if we have this situation where we've got this set of standards, of proliferated standards, and we've got pairwise connections between the proliferated standards. Now imagine I need to go from Lego to whatever it is that thing is on the bottom. Well, we could sort of compose them all together into this Franken connector, which is truly awful. But we could realize that with modern tools, we could synthesize down a specification for a direct connector between the two, and then just 3D print that direct connector. And that's the thought that Stitches had. That's the thought that this DARPA program SOCITE had, that you could actually have proliferated heterogeneous standards, and you could still have interoperability by post facto generating that interoperability on demand. And because everything was automatically generated, there was no efficiency loss. And in fact, the end solution is more efficient than forcing everyone onto the global standard. Okay, so forms of architectures used today. Let's talk about how this all comes together. And there are four main classes of architectures, MOSA architectures that are used today that I see. There's probably more, but these cover the vast majority of the cases. So let's start with the ossified MOSA. And if you can't tell from that name, I'm pretty biased on these things, and I'm pretty open about my biases about which ones are bad and which ones aren't bad. And ossified MOSAs are pretty much the worst. These are the top-down mandates to use consensus-based standards. This appears to achieve the MOSA goals, and in the short term, it sort of looks like it does, but in reality, it's the worst form of MOSA. It creates enormous ossification and stagnation that gets worse over time as the MOSA becomes locked to the standard, or you break the standard with each revision and you don't get an actual interoperable architecture. You just get proliferated standards that pretend to be interoperable, but don't handle the post facto integrations because they think they're on the same standard. So the second class that we see sounds almost oxymoronic. It's the proprietary MOSA. So how do you be proprietary and open? That's a little weird. And in this case, it's a proprietary infrastructure with open modular slots. And this allows for commercial investment to facilitate competition for everyone else. And we've seen this commercially. The most obvious examples are Apple's App Store and Google's Play Store, where they own the monopoly on their proprietary infrastructure, but everyone else needs to compete the slots. This is also a favorite of new primes in the DoD, where they like to claim that they're MOSA, but in fact, they are proprietary in their architecture. And this creates a vendor lock on the architecture itself, which is important because when we think about the most significant advances, whether in the commercial world or the DoD world, they're almost always at the architectural level. The iPhone was so different because it wasn't better parts in a normal touch-tone phone. It was because it was a different architecture for a phone. So I think the proprietary MOSAs still act like a proprietary solution more than a MOSA solution over any reasonable time frame. Then we've got a set of do-anything architectures, which are MOSA, but they're really OSA more than MOSA. They use very flexible commercial solutions, often open source, with almost no constraints. Things like JSON over Kafka. If you don't know what JSON over Kafka means, JSON is a technology that lets you sort of self-describe your messages, and Kafka is an open source solution for sending messages and disseminating data. That's got some very nice properties. It's scalable, it's resilient. It's a lot of good things to it. And these solutions are definitely open. They are completely open and they avoid all the different lock-ins. So that's awesome. But what they lack is the modularity. They don't provide the specificity that allows for great engineering of complex systems. They don't manage that complexity. And that makes testing, validation, developing complex systems all extremely problematic. And then the last one is the evolvable MOSAs, where this is sort of what I described up above, the post-facto integrations, where you expose the modular interfaces. You have modular interfaces, the modules, and you expose the modular interfaces, but you do so without broad mandates for standards. You acknowledge there will be a proliferation of standards, you accept that, and you properly handle it. The key here is that you force modularity where it's appropriate, and you force the open publishing of specific interfaces appropriate for this particular problem, and then you generate that post-facto interoperability. So as I mentioned, DARPA SOSITE program was the one that came up with this idea. Stitches is an example of this approach. If you're interested, as Arun mentioned, Jessa Lee gave a previous ETI Tech 101 on creating interoperability, and you can see that for more details. All right, so assessing these different forms of architectures, you can guess where I stand just by the way that I framed it. The ossified MOSAs, they can be useful when you're trying to interface with legacy solutions that are on existing standards. It's still not usually the best solution, but then it's a reasonable solution, but it will completely cripple an organization that uses it in the long run, as it always leads to standard lock until you finally crack and then break interoperability completely. On the proprietary MOSAs, these can be used for fast starts to capture market share. It eventually leads to vendor lock, which is great for the vendor, but not so great for everyone else. The do-anything architectures are great for simple problems, web interfaces, streaming data, but you should probably avoid them for tactically relevant solutions that require tight couplings, reliable timings, or security properties, because it's really hard to make those guarantees with these sorts of very loose architectures. And then the evolvable MOSAs, this is the form of architecture that provides both modularity and openness without creating neither a vendor lock nor a standards lock. And oddly enough, the law says that this was what should be used in a DoD program. So if you look at 10 U.S.C. 4401, you'll see that. So that's what I've got on the next slide. So what does that law say? It defines a modular open systems approach that is going to have modules, and it's going to have modules with modular system interfaces. And the way that it talks about the modular system interfaces, it says that it's one of two things. Either if they're available and suitable, you comply with the widely supported consensus-based standards. That's how you interface to the legacy fleets that already exist, because we can't afford to upgrade everything at once. Otherwise, you deliver it using what I call incremental standards. It's a little wordy in the actual law. It's pursuant to the requirements established in Section 804 of the National Defense Authorization Act of 2021. But really what that comes down to is you need to have a machine-readable format. And that machine-readable format needs to define, one, the syntax and properties. So what is the message? What is in the message? Two, a relationship between the delivered interface and existing common standards. That was like the connector between the Lego brick and the Lincoln Log. And then, of course, since humans are not typically proficient at reading machine-readable formats, document the functionality in a more human-readable format to say what it's supposed to do. So despite all of the confusion and the guidance, the law is very clear on what you should do. You should use consensus-based standards when they're available and suitable. And again, if you've got a really good standard that other people are using, feel free to reuse it. There's no statement that you shouldn't use standards. It's that you shouldn't force people to use standards when they're not applicable or when they're not appropriate. Okay, so I'm going to let the questions come in because I'm seeing a couple of questions, but I'm going to answer them at the end because we're almost at the end of the brief, and then I'll take all the questions together. All right, so a final thought, other things that aren't MOSA. For some reason, many other completely unrelated ideas and techniques get coupled with MOSA. If you look at the DoD guidance coming out from senior leadership in the DoD, you see a lot of this. And it really confuses me, to be perfectly honest. Things like DevSecOps, CI/CD, digital models and digital twins, product roadmaps, containerized frameworks, none of these have anything to do with MOSA. You can use them. They're fine. They're useful. Or don't use them as appropriate for your problem. The use of MOSA has nothing to do with these elements. I can do MOSA without doing any of these things. I can do MOSA while doing some of these things. I can do MOSA while doing all of these things. And I can do any of those things without MOSA. So they are fully modularly decoupled. And if you believe in MOSA, you should decouple them. So it is rather funny to me that the DoD guidance on MOSA says don't use a modular approach in your development because it couples things like DevSecOps and CI/CD with MOSA. The whole thing is just confusing. And the problem here, of course, is that expanding the MOSA requirements create barriers to adoption when basic MOSA requirements are remarkably easy to meet. Put modularity where it makes sense, publish the modularity that you put in. And if you just do those two and do it in a machine readable format as per, NDAA section 804, 2021. And if you just do those two things, you really are doing most of MOSA. You're getting the major benefit of MOSA. And if you don't know what your modularity is, and you don't know what your interfaces are, you should probably pause and get that straight before you build your system. And by the way, this was an item that was raised by the GAO report, and it was raised in the discussion that Arun had recently on this topic on a previous webcast. So it does come up a lot, and it's often used by the program offices as a sort of an excuse for not adopting MOSA, is that MOSA is too expensive. And that's usually because the guidance is said to do a lot of other things that aren't MOSA with it. Okay, so summary and conclusions. MOSA provides two key architectural constraints: modularity, which separates concerns, allows us to solve each part of the problem separately with different experts and then bring them all together; and openness, to expose the modular interfaces that you have created to allow broader competition. It's not about everyone agreeing on the global standard. And when MOSA is done right, it provides enormous benefits. Mostly that it reduces the complexity of the solution to allow you to build faster solutions and evolve them more efficiently over time. And it improves competition to reduce cost and encourage innovation when you do it right. But standards are the problem with MOSA. They're certainly not a feature of it. They create the ossification and the stagnation. They block the innovation. And the reality is exposing the modular interfaces is enough to both achieve the benefits and be compliant with the law. And fundamentally and finally, using MOSA requires very little extra effort. Much of what is normally included as part of MOSA guidance is not required for MOSA. And if you're choosing to do MOSA on your own, there's no need to couple that with modularity and openness. So with that, I'll stop and take some questions.
Great, thanks for that, Evan. There's questions coming in. Please type in your questions in the question and answer box on the bottom of your webinar screen. I will start with a couple that are in my head.
Okay.
Based on, like you said, we did a couple of podcasts recently on MOSA, and please go find those, Emerging Tech Horizons, and Evan was a guest on at least one of those podcasts. When we think about this in terms of the DoD context, it sounds expensive. And so how does this fit into program costs, either upfront or over the life cycle of a program?
Yeah, so I think if it's done right, it should not be expensive. It should actually reduce costs from day one. If you layer on a whole bunch of other things, then it will become very, very expensive. But if you think about how I described MOSA, it's got two parts. You need to understand your problem well enough to know where it's tightly coupled and where it's not tightly coupled. If you don't know that, you probably shouldn't be building your system. And if you do know that, it's sort of easy to define where the coupling is. Most people already do this, whether they think they're MOSA or not. They build a system architecture, they define the different elements, they have leads for each of the different elements, they have contracts for what those elements are going to consume and produce. And so MOSA is really about, think about where that modularity should occur. That's doing your system architecture work, which every program does right now. And then document whatever decision you made in a machine readable format. And you can use lots of different machine readable formats. You can use Google protocol buffers if you want. You could use the Stitches machine readable format. You can make up your own machine readable format as long as you tell me what it is. So there's lots of flexibility in how you implement it such that it is already part of your natural workflows. And when you do that, you'll get the vast majority of MOSA for almost no additional cost, and you will get benefits because you will now know what your interfaces are, you'll know what your interactions are, you'll know what your architecture is, and as your engineers move on and off the program, which they eventually will, you'll have continuity between them. So it's almost zero upfront additional cost, and it is significant lifecycle benefit costs. Now, the problem is when you couple in DevSecOps and CI/CD and digital twins and project roadmaps and all these other things, those get very, very, very expensive in their upfront costs. And whether or not you're going to recoup those costs is an open question depending upon the problem. But MOSA doesn't fall into that category, in my opinion.
So all that sort of leads you to say it seems like MOSA might be counter. It's good for the customer. Is it so great for the supplier? So what's your sense of why a supplier wouldn't want to try to avoid their customer using MOSA? Why wouldn't they try to slow roll MOSA?
Yeah, it's a great question. So it's a funny thing. When I started down this path long ago, I presumed there would be lots of people who wouldn't like MOSA, which is the basis of your question. And then this really weird thing happened, which is that if you think about it from the platform integrator's perspective, so if I'm a big prime, and now I use MOSA on my subs, well, I obviously am getting a benefit because I now know what the interfaces that my subs are using. I know what role they're playing, and if I need to replace them, I can. So it's clearly beneficial to the primes to use MOSA to control and manage the risks and the challenges on their subs. But you get a really funny effect on the other side, which is the subs want to be able to sell their boxes to multiple primes. And if you use the global standard, or if you let the prime sort of come up with their local platform standard all the time, then the sub has to basically have a non-recurring cost attached to each of their sales. Whereas if you just let the sub expose their interfaces of their box, as a modular open systems architecture approach would allow, then they can sell the same box to lots of different primes without incurring that non-recurring cost on top of it. So the subs can actually get an enormous benefit as well from MOSA. So you get this really funny effect that if done right, i.e. you're not using the global standards or the consensus-based standards to lock everyone up, everyone's non-recurring costs go down and everyone makes more profit. Whereas if you do it wrong, everyone makes less profit. And so that's why I made that opening statement that if you put in the right amount of MOSA, I think it's really easy to adopt, but if you put the wrong amount in, everyone hates it.
So there's a lot of questions on cost coming in. So one is, are there published examples of cost benefit analysis of MOSA that we could direct the audience to? Are there any aspects that are controlled by the scale of the system that it's trying to be applied to?
Yeah, it's a great question. And unfortunately, that's not my area of expertise in terms of like GAO reports. So I don't know if a systematic study has been done. And even if it has been done, I think it would be really hard to not conflate the things that are not MOSA that people do with MOSA. And again, we're on an open line, so it's a little bit harder. But what I can say is that DARPA definitely went through and did a series of experiments. And in fact, I think DARPA presented at an NDIA conference around 2019 on the series of experiments to show the speed and cost benefit of doing this sort of heterogeneous MOSA approach. So I think that's where I would look to see if I could find some data. When I think about good MOSAs and where they're actually working well, where I would look at like the TAC community, the tactical assault kit community, that the Marine Corps uses a lot. They do a really great job of doing sort of heterogeneous MOSAs. And that's where I would look for a good example to sort of see the scale and cost impacts.
Another question. Does the use of the more open interface systems in defense systems create any kind of cyber vulnerabilities, especially if you're using publicly available interfaces?
Yeah, so that's a great question, and it's a little bit counterintuitive. So if you adopt the standards-based version of MOSA, then I think it can add to your cyber vulnerabilities because you're basically creating a homogeneous attack surface where if you find a vulnerability in one, you're likely to find a similar vulnerability in many. And those sort of systemic cyber vulnerabilities are the ones that are most critical to be afraid of. If you're using the heterogeneous MOSA, the evolvable MOSA, then each system has its own interface, and that interface is as specific as possible, which means that the code that's processing that interface is as clean as possible. So we often talk about the fact that the worst thing that you could possibly do is make your front end code that has to parse your messages parse an arbitrary message like a JSON message. It's absolutely a nightmare from a cybersecurity perspective. But when you do the evolvable MOSAs, you can get your message structures to be very, very, very specific and narrow, which makes your parsing code much cleaner and smaller. In fact, it doesn't even have to be Turing complete in most cases, which allows you to have much more secure interfaces and bottlenecks. And this was shown, a similar thought was shown on the DARPA HACMS program about a decade ago, where if you could put in a really clean, specific choke point, you could get enormous security gains on your systems. So oddly enough, the evolvable MOSA approach boosts your security substantially. And in other settings, I can probably talk about more of those details.
Another question. Any difference between trying to apply MOSA to hardware versus software systems?
Yeah, that's a great question. So long ago, I think there was no difference. And then software took this leap forward where academia and the commercial world created a set of technologies and tools around creating domain-specific languages and compilers, optimizing compilers for those domain-specific languages that allow you to take these sorts of graphs of relational specifications and compile them into very highly optimized components. So I think software systems took a major leap forward in how well they could handle evolvable or heterogeneous MOSAs. Over time, I think the hardware folks are catching up between 3D printing and on-demand manufacturing. And I don't know if the hardware side is going to fully catch up, but the more you can do the on-demand generation of the components, the closer the hardware will get. But at the moment, the software has an enormous advantage on the modularity that I've seen because of this ability to do the post-facto generation of the interoperability software.
You talked about the US code, 10 USC 4401. The question here is, how can that piece of law be enforced if, and you've touched on this too, some
Yeah.
offices and vendors are trying to pursue standard locks, right? Or vendor locks. So what's your thoughts on how this mandate, which I think you endorse, can actually be enforced?
Yeah. So again, I'm an engineer at heart, so I'm not really the legislation guy here, but I would say a couple of things. One, the legislation requires that DoD set up a repository. That was another part of the law that I didn't quote, and that programs needed to post to that repository. Now, if the DoD guidance had been, we're going to set up the repositories and programs will have to post, then contracting officers can enforce that by putting in clauses that say that the vendors simply will not get paid their fee until they comply with the requirements of the contract, which include posting their heterogeneous MOSA interfaces to the DoD, federated DoD repositories. So it would be very easy to enforce if the executive branch chose to. Now, the previous executive branch did not choose to. They went in a different direction. They're fighting that standard. And when you look at the guidance, it basically says, no, we're not going to do what is, to me, pretty clearly the intent of 4401. Instead, we're going to focus on everyone doing global standards, consensus-based global standards. And with the DoD guidance currently being in opposition to what is, to me, the pretty clear intent of the law, I think enforcement is hard. So I think the two sides are going to have to get together and hash this out. I don't think enforcing it with the vendors is hard at all. I don't think enforcing it with the program offices is hard at all. You literally just put clauses in the contract to say that you have to publish your heterogeneous modular open system interfaces into the repositories as per the law. But both Congress and the DoD leadership, the executive branch, have to agree on that first.
I think you answered the next question in advance. How does one contractually specify MOSA requirements? Which is basically you can even lift the language from the law itself.
Yep.
Is there a set of regulations that have been written as a result of the law that contracting officials could look at to find contracting language?
So oddly enough, if I remember correctly, the NDAA 2021 Section 804 put in requirements for the DoD to do certain things at certain times, and the DoD has pretty much just ignored all of that. So I don't think there's a series of regulations. I don't think at least I don't really know of the official federated repositories of MOSA interfaces. So I think the challenge right now is that the DoD guidance is not helping the program offices and the contracting officers put the right language in. Now, for contracting officers that want to put the language in, it's relatively straightforward to put in the language saying, in the data rights terms, saying that these interfaces are non-proprietary. So in other words, there's government unlimited rights on these interfaces, and that one of the deliverables is the delivery of all of your modular open system element interfaces, and that make that a deliverable. And once you've done that, then you've got a lot of contractual mechanisms. We've known how to do this for a very long time. Contracting officers know how to do this already. It's a pretty standard thing to enforce these data rights. It would be nice if we had a canonical example to reuse, especially on the non-FAR-based contracts, the OTs that have become so popular now. But right now, I think the contracting officers have to do a lot of work themselves because the guidance is pretty poor.
Okay, follow on to that then. Is there any guidance on pricing this kind of thing if you want to write it into your contract?
Yeah, so it's an interesting question. Obviously, when the government puts out an RFP, they're going to put in requirements, and some of those requirements will be to have modularity at particular points that the government has decided are critical for the program. And then the contractors are going to have to put forth technical proposals to solve that problem. And part of those technical proposals will be architectures that will almost certainly look modular. When we look at the system architecture diagram, you're going to see modules, you're going to see interfaces, you're going to see messages passing between them. And so specifically putting in the cost of documenting the modular interfaces in a machine readable way is something that I think is really important that contractors should do to show that cost. And then to show the cost of the modular integrations, because if you've got a modular approach, you have module development, and you've got integrations, and those are separate tasks. So any sort of sane work breakdown structure would include tasks for development of each of the architecture, development of each of the modules, and then integration test validation of the integrated capability. So I think pricing becomes more straightforward in a modular approach because the work breakdown structure and the basis of estimate of those elements becomes naturally more granular and naturally more defensible through historical realities than if you were to do a big ball of here's a crazy architecture that couples everything together. We're not going to reuse any specific module without massively changing it. And if you look at any of the costing modules, like the old Kokomo models, they just don't know how to estimate cost in that environment. Whereas these cost estimating modules are very good in modular approaches.
A kind of related question. When planning on using this kind of approach, should people be doing market research to see if there's an existing commercial standard or an existing commonly used private industry standard?
Yes, it's a great question. The answer is absolutely, absolutely yes. For those of you in the DoD, I go to stitches.mil. That's a government site run by the Air Force that contains a huge repository of existing standards, both officially blessed ones as well as ad hoc ones that people have come up with. And whenever we do these programs, the first thing we do is we hop on there and see what other people have posted. It's an open forum where many companies post their modular interfaces. And we go sniffing around everyone else's modular interfaces to see if they've got something we can start with or something we can use. We'll often do a small adaptation or tweak to it, but it's way better to start with something that's tested and true before deciding you need something different rather than just assuming you're going to do it clean slate each time.
Okay, and last question. Looking back in history, what programs do you wish had used a MOSA approach? If people will recognize that, gee, things didn't go well, and you can kind of tie that to a little bit their lack of use of MOSA approach.
Oh, that's a tough one. I'd have to think about that. I think FCS, the Army's Future Combat System, is the most obvious one. It represented one of, if not the largest attempts to reorganize the way that we build systems, and it was distributed. So it really needed modularity to tame the complexity that was inherent in it. But I didn't see a heavy use of modularity there. I think when we look at the JADC2 programs today, I think that I'm extremely concerned that the JADC2 programs are using the ossified MOSA approach rather than an evolvable MOSA approach. And I think we've already started to see the problem that even if the Air Force and the Navy independently come up with a solution for JADC2, there's a J in the name. It's not SADC2, it's JADC2. It's joint all domain. It's not service only all domain. And when it goes out to a COCOM and they have to now bring those systems together, you really see the damage that can occur if you haven't embraced the idea that you're going to have heterogeneous proliferated standards throughout your systems. So those would be the two examples I would probably look at more carefully to decide if they were good examples.
With that, we're going to have to close the presentation. Thanks very much, Evan, for that great presentation. Thank everyone for their attendance and all the great questions. We're going to post the recording online and the slides as soon as possible. If you have feedback about this event, especially topics you'd like to see us cover in the future, please email us at eti@ndia.org. I want to take a minute to highlight a few upcoming events. The next Tech 101 will be on cloud seeding technology on May 14th from 1 p.m. to 2 p.m. with Dr. Edward Rice from the Government Accountability Office. Additionally, ETI has some great upcoming webinars in May. Outcome-oriented approaches to successful software acquisition, which we're doing in conjunction with Carnegie Mellon University Software Engineering Institute, is on May 6th. Policy modeling, navigating uncertainty using simulation as a tool for policy innovation, which we're doing in partnership with the University of Central Florida, is on May 22nd. And then a webinar on quantum supply chain vulnerabilities, especially with respect to NATO partners and allies. That's on May 28th. Be on the lookout on NDIA's calendar of events page for more information on all of these events. Then I want to highlight the Emerging Technologies for Defense 2025 conference. Visit ndia.techexpo.org for more information. We're putting together a great conference with keynotes, breakout sessions, industry government speed dating sessions, and opportunities for exhibits, demonstrations, and technical presentations for the NDIA membership. For more information, again, please visit ndia.techexpo.org. And finally, we mentioned it in the 101 today, the Emerging Tech Horizons podcast. We've got 2 recent episodes on MOSA, one with Evan talking about progress being made and one on the GAO report on MOSA. Please visit this QR code or wherever you get your podcasts, YouTube, and the other platforms. You can visit our website for more information on that. To learn anything more about what's going on at NDIA, including our activities, our divisions, and how to become a member, please visit ndia.org. Thanks again for joining us today. Thanks again to Evan.